take it away.
Thank you so much for the great words. Okay, so let's talk about some hybrid RL today. So I guess we covered many beautiful things in RL so far, like policy gradient and model-based learning, imitation learning. And today we're going to make a few two departures, actually. But trust me, this is something that works well in practice and has some great principle guidelines. So let's dive in. So the first departure that we're going to make is we're not going to do purely online RL anymore. So we're going to assume that we're going to have like some offline data. Think about, I guess, like teleop data when you want to train some imitation learning data for robotics, or like just the YouTube videos. And so concretely for offline data, it's something slightly different from expert demonstration. So we're just gonna assume that we have like an offline distribution of state action. So, and we're gonna sample, or let's just assume reward is deterministic. So we're gonna have reward and also samples from the state transition. So basically we're gonna have like a data set that looks like this. So you're gonna have like state, action, reward, next state. So as you can see, different from expert demonstration, I don't tell you anything about the quality of the data distribution mu. I'm only saying there is a distribution that generates state and action. And you basically, like, if I don't tell you anything about the quality of this distribution, if you do imitation learning, either Dagger or behavior cloning, you will just get another policy pipe that just mimics the distribution of mu. No guarantee on the performance. And let's leave the offline data part here for now. And another departure that we're gonna make is instead of learning a policy or learning a dynamics model, we're gonna do value learning. So I guess we covered value iteration in this class already. So the idea of value iteration is, say, basically I want to, if I gave you the optimal Q value function, Q star, and then I can just get my optimal policy by saying, okay, I'm just gonna look at my Q star, and I'm gonna take the best action according to Q star, right? So the idea of value iteration is basically so recall the Bellman operator, let's just call it T, and I give you a Q function, and I query it at a state and action pair. The Bellman operator is basically what is the one-step backup function if I act according to this value function and according to the transition dynamics. All right, hopefully everyone still, thanks. Hopefully this is still familiar to everyone. So the idea of value iteration is basically I'm gonna iteratively do the following step, right? I'm gonna learn a Q function by iteratively applying the Bellman operator on the Q function on all state and action pair. And this process will terminate at some point. And you will have like a Q value that is at the end, like your Q value will be approximately Q star, and you're done. So if you learn a value function. that's basically it. So what is this process doing? This process is basically, if it's trying to minimize the difference between a value function and its Bellman backup, right? So let's just call the difference between, say, a value function, let's call it f, and the difference between its Bellman backup as the Bellman error. And remember a property of the optimal Q function. The optimal Q function, when you back up the optimal Q function, it will return you exactly the optimal Q function itself, which means the Bellman error of the optimal Q function is zero. So again, the idea of like value iteration is like if I iteratively minimize my Bellman error, my learned value function will be approximately close to the optimal Q function. And basically that's the idea of value learning. If I learn something that is close to the optimal Q value function, I will get an optimal policy. Okay. So far so good? Okay. So remember, when I do value iteration, I'm actually doing planning, right? I know exactly the transition dynamics. I can query state and action anywhere. So what I do is like for all state and action, I'm gonna try to do this iterative Bellman error minimization process. But in reality, I don't have like a simulator. Most times you don't have a simulator. So I can't just arbitrarily query all state and action to minimize the Bellman error. And in fact, you don't have to have small Bellman error everywhere. By everywhere, I mean on all state and action pair to have a guarantee to say, okay, I'm gonna return a good policy. So the question then becomes, okay, another Q. This is question, this is not Q function. So the question is, where should I minimize my Bellman error? So let's don't think about the online setting for a bit. So let's just think about, okay, go back to the offline setting. So what kind of data set, if I gave the data set to you and you minimize your Bellman error on the data set, I'm gonna have a good guarantee, okay? So let's start with the most naive setting. So let's say for my offline distribution mu, the offline distribution mu covers everywhere. So what does this mean? So this means for all state and action, this ratio is at least, let's say, some constant C, right? So if I query any state and action, the probability mass of the state and action is not zero. So you always have some data for each state and action in the data set. Okay? This is like kind of I guess the best kind of setting you can hope for because I already gave you data everywhere. You don't have to do exploration or online rollout or learning. Okay? And I'm gonna try to learn a good value function in this case. Can I do that? So guess the answer is pretty obvious. So there's many ways to do this. So
do you mean less than C?
Right. Yeah, so like if mu SA is 0, then this guy is like infinite, right? So we want this ratio to be bounded. So what can we do? So we can, one very simple way, if we kind of connect it back to what we learned in the model-based lectures, is like, what if I just learn a dynamics function given the data set I have, which is the transition dynamics is just number of samples of S prime, SA, S prime, divided by the number of samples of SA, right? I learn the transition dynamics according to the data I have. This is the most naive estimation you can have for the transition dynamics. And then I just do whatever, like planning in my learned transition dynamics. For example, I do value iteration according to p hat. Does that make sense? I learn a model, and then I plan in the model, like purely model-based RL. So I will get like a Q value function, Q star, P star, which is like I, for example, do value iteration in the learned model. And what does this learned value function tell us? So I'll state the result first. So something you can say about this Q value function is, if I say I define my learned policy pi hat, which is the greedy policy, according to the learned Q value function. Okay. Argmax. Okay. What can I say about this learned value function? So turns out it's pretty close to the. Okay, actually there are two results that I need to state. So the first one is, if I have a lot of data, if you look back at the transition dynamics that you estimated before with my offline data, since my offline data has coverage everywhere, so one thing I can say is, for all state and action, your learned dynamics is pretty close to the true dynamics. For example, in the TV sense, okay? So basically here, if you look at the result, it's quite intuitive, because like n here is the number of samples that you have in the whole data set, and C is the coverage coefficient, and you can see like my error will be bigger if my coverage coefficient is big. For example, like if we take things to the extreme case, if there's any state and action that I don't cover, my C will be infinite. And this is saying, okay, you cannot guarantee that your dynamics transition estimation is close to the true dynamics of the MDP, right? So, but the more data, if everywhere is covered, let's say C is bounded, then the more data I have, the more accurate my estimation on the dynamics will be, right? Very simple. And once we have the goal of model-based learning is like, I want to learn accurate model, hopefully everywhere. Don't have to be everywhere, but now we have the ideal case that the model is accurate everywhere. Then we can basically just let me see. Okay, let's just do the proof real quick. So now I just want to bound the Q value of the optimal policy and the Q value, the performance of the learned policy, right? So this Q is the Q value according to the true dynamics, and I want to compare the performance between the optimal policy and the learned policy that by doing safe planning in the learned dynamics, right? So I can simply bound these two terms by, say, I stick in another term that is
It helps you when you did the proof of simulation on the last lecture.
oh, we proved simulation lemma? Okay, great. Okay, gonna save 10 minutes.
Always happy to do that.
Right, I just subtract and add this term, Q hat, according to the optimal policy, right? So there are two things you can see here. So if we look at this term, then this term is always smaller than 0 because because this term is not smaller than 0. Okay. Oh, so not this term. So if you look at this term, right, I'm gonna replace this term by something larger, okay? So here, this term is saying, okay, what is the estimated Q value of the optimal policy, right? I'll replace this optimal policy by the learned policy, which is the greedy policy with respect to the Q hat, right? So this term always upper bound the Q hat pi star because again, like pi hat is the optimal value according to the learned Q value function. And now we have this difference, right? And this difference. And these two differences are just, okay, what is the Q value difference between if I act under the true dynamics and the estimate dynamics according to the same policy, right? So Q pi is fixed and Q hat is fixed. And the value functions are different. So then we can just apply the simulation lemma that we covered in the previous lecture. And this is just bounded by 2 times 1 over 1 minus 1 minus gamma squared times the QA distance, your learned dynamics error, which is f star, right? So then we have the guarantee for the most naive case, which is you have data everywhere. But this is like a little bit strong assumption to say. Like in this case, you can see like there is not that much difference between if I give you a simulator and just let you query arbitrarily state and actions and the next state dynamics. So maybe now let's consider something maybe weaker. So let's define something that is the visitation distribution of a policy. Do they know this?
Yes.
Okay.
And by the way, most of the lectures are done in the finite horizon on this campus.
So like,
Okay.
But it's fine to just.
Yeah, so like rule of thumb is like, in general, the translation between like discounted setting and finite horizon setting is like 1/1 gamma is just h. So most of the time you can switch between these two. Sometimes you cannot, but. So this is just the visitation distribution of state and action pair. It's like, oh, okay, what is the probability of like you visiting this state and action if I give you a policy and start at the initial state? So something that is weaker than this is, okay, what if instead of the offline distribution covers everywhere, it only covers, say, some policies visitation distribution, right? So I'm gonna generate a bunch of policies. Like all I need to do is like, I have some accurate estimation under the policies that I care about, right? So I guess a weaker notion of this is called all policy concentrability. Which is saying, okay, for all pi, the worst case ratio between the state, between the visitation distribution of the state and action of the policies that I might care about, and the offline distribution is bounded. So,
can you tell us when all policy concentrability is weaker than the first one?
okay, so because this is the probability, right? This is a probability distribution. If I query any state and action on any policy pi, this term, this is always bounded by 1, right? In the finite horizon case. So, like, at least this is a smaller term than this one. And it's a weaker condition, right? I don't have to cover the state and action for everywhere. I just need to cover the state and action where the policy visited. But, okay, one may say, okay, in some like situation, like, for any state and action, like there always exists a policy that goes to the specific state and action, right? So in some sense, this assumption is also really, really strong. So we don't want to deal with this later, as we will see. But for now, let's see. If I gave you this, like, what can you do, right? So it turns out, if you want to do value learning in this situation, you can have something that is very, very simple. Okay, so let's start with some setup. Again, I want to do value learning, right? So the goal is to learn a value function f that will, say, approximately be the Q star function. And to learn then like it's like classical learning theory is like, then I need a function class, right? I need a function class. So the function class here, instead of a class of policies, in this case, we're just dealing with a class of value functions, right? So I'm just gonna call this set of candidate value function as calf. And there is actually something more that you need. We need to say something about the value function, which I will tell you later. I'll tell you the algorithm first. And in the discounted setting, it's easier to stay in the discounted setting. So let's see. So in some sense, it is very similar to value iteration. Okay, so the algorithm is called fitted Q iteration, FQI, which is basically saying I'm gonna iterate from iteration, say, t from 0 to t, okay? And each iteration, I'm just gonna learn a new value function that minimize the Bellman error given the previous value function. Of course, under the offline data. Let's see.
So do you guys remember the lecture you gave on class and faults iteration? It's a much more clean way of stating what you're talking about there.
So let me make some highlights. So the target of, like, if you look at this objective, basically it is just doing some least square regression, right? So I have some target that I want to fit, and let's just say you can think of this as fx, right? And this is y. So I just want to do some least square regression from x to y, where I want to find the best regressor f that minimize the square distance between fx and y, right? And here y is just the Bellman backup of the value function that you learned in the last time step. And the best regressor that I'm gonna have, that will be my new value function.
So how's the stuff inside square Bellman error? Is it the next state?
Yeah, you want to minimize you want to use your current candidate value function to minimize the Bellman. It's not the Bellman error.
I see. I missed the Bellman operator.
Next state, yeah.
Yeah, there is a Bellman operator here.
That don't look like the left hand of the square bracket.
Yeah. Right, so this is like a fixed target, and I just do least square regression with the target being I want to mimic the Bellman backup of the function of the previous time step. Given my data. Oh, yes, here. Yeah. Here, this like expectation is basically the empirical expectation that I sample data as a R S prime over there from my offline data set. Okay, I just minimize the Bellman error over my offline data set, and that's it. Okay, so So now, like we can think about why this algorithm requires that the offline data set covers all policy, right? So at each iteration, I will induce a new value function. And the new value function will induce a new policy, right? You don't know where exactly this new policy will visit. And I want to have some guarantee that during my learning process, my Bellman error, this is not exactly Bellman error, but this square error will be small, right? If this square, let's say if the offline distribution does not cover some policy that is induced during your learning process, then at that iteration, there is no hope I can say this Bellman error will be, this error will be small, right? So, and there's another, the error, the empirical error you see will always be small, but it will not reflect on the true distribution you see if you roll out the learned policy in practice, because there will be a distribution match between your offline data set and the real policy that you're going to roll out after you learn the value function, right? So basically the intuition is I want the offline data to reflect the distribution of the policy that I learned. And if the offline data covers the policy, only if the offline data covers the policy's distribution, I can guarantee that. Otherwise, there will be, we've been seeing so many times of covariance shift in this class, and you know what will happen. So, but there is another thing that is missing here, because again, now you can think of we're doing some sort of supervised learning, right? So it seems like there's something that is still missing here, because in supervised learning, okay, you can always do the agnostic case, but then you need to pay some misspecification, right? So seems like we're missing some realizability assumption in this case, right? So who tells you that if I find a policy in my policy class, it can always regress to the target Y, right? No one tells you that. So this brings on another assumption that we almost always need when we do value learning. That is Bellman completeness. So this assumption is saying for all value function in my function class, the Bellman backup of that value function is also in my function class. So they don't have, they are not the same function, right? The Bellman backup of a function is not the same function as the function that's being backed up. Only the optimal policy, optimal value function will have that property, but this is basically a realizability kind of assumption so that we can ensure this regression problem is realizable. Right?
How strong is this assumption?
Very, very strong.
Linear doesn't satisfy it.
Linear MDP satisfies that. Linear Q star does not. Because in linear MDP, your dynamics is parameterized by the feature, right? If you do one step, it's just you can incorporate the next step value function into the predictor. So you have WQ something. So tabular MDP satisfies this assumption, and linear MDP, which, well, do they know what that is?
No, I think we're pretending everything the tabular MDP in the entire course.
Okay, great. So tabular MDP satisfies this assumption. Neural network does not satisfy this assumption. Yeah, in general, it's a pretty strong assumption that people are trying to get rid of. and at least personally, I think Drew hates this assumption very, very much.
Which is why he didn't mention it, even though he was making it in his lecture. But I think maybe one of the things to think about why this assumption is particularly strong, right, is that if I expand the class of f, like I make it bigger, this assumption can go from being true to being false, right? Like I can add an extra value function, but if that value function's Bellman backup isn't in the same class, now this assumption is false, right? Because for other kinds of realizability, right, let's say like you want to have your expert policy in your policy class, right? You just make the policy class bigger, right? You add more features, use deeper networks, you can get closer and closer to being the realizable setting, like the optimal thing's actually in the class. But here, if I make the class bigger, this can actually become false. So as you have sort of over-parameterized deep networks, it becomes a worse and worse assumption, because you have to assume this kind of like crazy property.
Yes. Okay, now we have all the ingredients. So I'm not going to prove for this. You can kind of convince yourself it's like something similar will happen. Like the value iteration in this case. It's just instead of I'm going to query all state action myself, I'm going to do some kind of like a supervised learning version of the iterative Bellman error minimization. And if I satisfy the strong coverability assumption and the realizability assumption, then you can kind of convince yourself the error will converge, and the estimated value function will converge to the optimal value function. Okay? But again, it's still like I said, in the worst case, there is not that different between these two assumptions that we just made. Okay? And finally, it brings to the most relaxed setting, and we're finally going to talk about some hybrid RL. So right now, everything is in the full offline setting, right? I gave you a data set, and you minimized the Bellman error for me. So the most reasonable kind of offline data property is called single policy coverage. Which is saying, okay, there exists or for a policy that I care about, the concentrability between the policy that I care about and the offline data is bounded. Okay, I'm gonna annotate the coverage coefficient by pi. Like whatever policy that I care about, this ratio is bounded. So basically this is sort of like moving from for all to there exists, except like you kind of pick the policy yourself. So if you want an easier understanding, we can just say, okay, if I only care about the optimum policy, so I just say like the ratio between the optimum policy visiting traces and the offline data set is bounded. So if you think of imitation learning, right? Imitation learning, this ratio is always 1 because the offline distribution is collected exactly using your optimal policy, right? But here we're assuming something that is way weaker in the sense that like the offline distribution, the data collecting process doesn't have to involve the optimal policy at all. Like in fact, sometimes if you roll out a random policy, it might just cover the visitating traces of the optimal policy. So this is, I guess, the least strong assumption that you can hope for an offline data set. So does that make sense? So then like one might hope for, say, is there a purely offline algorithm that works only under the single policy coverage setting? The answer is no. So there is lower bound that say single policy coverage is not enough for offline, pure offline RL. And well, you need at least some kind of additional assumption. For example, like say your optimal value function has some kind of gap assumption, meaning that the best action and the second best action are very distinguishable, or some other more crazy assumption. So it's kind of sad that for example, like single policy coverage plus Bellman completeness does not work either. So it's kind of sad that purely offline RL does not work under the reasonable assumption. And I guess something that is even more sad is it also does not really work in practice as well if you want to do pure offline setting. Because, for example, if you say, I just want to run an offline algorithm, like in deep learning, it's like you don't, like you need to terminate your algorithm at some point, right? But if I only tell you, all you have is this data set. In fact, it's extremely hard to know when to stop your training and deploy your policy. So what do people do for offline RL in practice? Is I run my offline RL algorithm, I get a policy, I get a bunch of checkpoints, and I'm gonna roll out the checkpoint one by one online. And I pick the best one and say my offline RL algorithm work. So basically the validation / like when to start early starting issue has been bothering offline RL in practice as well. So as I just hinted, what people do to make offline RL work is maybe I just add some online flavor. And this exactly brings us back to hybrid RL. So the setting of hybrid RL is I gave you offline data, but I also gave you online interaction access. This is like perhaps what the paradigm where like most empirical success of reinforcement learning has been. If you think about AlphaGo, it has both expert demonstration and interaction access with the board. And if you think of ChatGPT, it's like I have the corpus of offline web data, but I also need to do fine-tuning with online RL. So magically, well, I don't know if it's too surprising or not. If you have online interaction access, then with single policy coverage, I can make things work for value learning. So the algorithm is extremely simple. So it's called hybrid Q iteration, I guess. And HiQ for short. So what does HiQ do? So remember we start with the offline data set, let's say D off. And we also have like an online interaction access. So what we do actually is very simple. Let's say we also like randomly initialize our value function f0, okay? So the algorithm goes like for iteration 1 to t, okay? I'm gonna first just let the policy be the greedy policy of my previous iteration's value estimation. Okay, maybe -1. And then I'm gonna roll out my current policy and collect data set SA, R, S prime. So this is the online data. Okay, and let's say I put them in a buffer that's called D-on. And what I'm gonna do next is I have this online data and I have this offline data, right? I'm just gonna do FQI on my combined offline and online data. And that's it. So that's basically the algorithm. It's like the only difference between HiQ and the offline version of PhysicQ iteration is in the hybrid RL setting, I will keep rolling out my current policy according to the value functions that I learned to collect more online data. And then I'm just gonna do this offline RL subroutine FQI to fit a new value function with the combined offline and online data.
You need to aggregate the online data sets over time.
Oh, right. So this kind of means, okay. Yeah, let me be more precise. So D-on will be D-on union the data I just collected. So I'm being a little bit lazy, but just think of everything in the finite horizon case. It's like I do this for every time step in H.
So what can you say rigorously compared to purely online algorithm?
Yeah.
So what's the sample?
It's a little bit subtle actually, which I'm gonna go over right now. So comparing to purely online, the learning goal here is actually a little bit different. It's more like a offline learning flavor goal. So that's offline RL. So for hybrid RL, the learning goal is to compare with the policy pi, the best policy pi that is covered by such that C pi is finite. Okay, so I tell you the offline data only covers a certain policy. And for offline RL, of course, the goal clearly is to compare whatever with the best policy covered by the offline RL. And one caveat here is for hybrid RL, the learning goal is kind of the same. You can only compare with the best policy covered by your offline data. You cannot always compare with the optimum policy, unless the optimum policy is covered. So this is like slightly different from the online learning objective, but there's like, right now we're just covering the most basic version of this setting. There are like more refined versions that actually let you compare with the optimum policy.
I guess in some areas, it makes a lot of sense here, right? In the sense that like, given we're not sort of assuming we get expert data, right? We just have this kind of batch of data we saw from somewhere, right? Who knows what's in it? So I think we don't want to compete with pi star, the optimal policy, right? We want to just compete against the best of what we've seen so far, right? So it's kind of like you were saying, it's like the same notion as offline RL in terms of the kind of target we're trying to go for, but we actually need sort of weaker notions of coverage in terms of what we see in terms of the data. We like the single pass up SBC thing is like, actually sufficient. Which I think is sort of what you want, right? Like you want, if you see the thing in your data, you can compete with it, right? That should be enough.
And also, like, should I briefly discuss exploration?
Yeah, sure.
So if you look at this algorithm, it's not doing any exploration at all, right? Every time I'm just do the most greedy thing that I can do, right? It's like, what if I just tell you that the offline data doesn't cover anything useful, right? Let's take things to extreme. So if you learn from something that doesn't contain any useful information and you act greedily with respect to that, like there's no hope that I will learn a policy that will let me compare with the optimal policy, right? So basically what happened in the more refined version is like they add more exploration flavor so that eventually you can compare with the optimal policy.
You remember the sort of, there was like 4 trees I drew in like the model-based RL lecture last time, right? Remember how like until we added in the hybrid data, we basically couldn't compete with the optimal policy? That was only if it covered that. The point you're just making is like, okay, well, even if the offline data weren't to cover it, right? Like if you add in some exploration bonus, you're able to actually get that, but you have to pay for that in terms of samples.
Okay, why should this work, right? So let's go back to the questions that we asked at the very beginning of the lecture. It's like, what are the sufficient distributions that I minimize? If I minimize my Bellman error on those distributions, I can have good guarantee, right? So of course, the sufficient is like all possible state action pairs. Or if you think of offline setting, it's like all possible policies traces. But apparently this is not like necessary, right? So this boils down to the analysis of hybrid Q-learning. I won't cover everything, but I will give you the overall idea that answers the question. So the key lemma for hybrid high Q is, I will say it first. So if you look at your error decomposition, you only need to have small Bellman error under the distribution of the policy that you want to compare with and under yourself, okay? So what do I mean by this? So let's call the policy that I want to compare as pi e. I don't know why we come up with this notation. Maybe we want to say expert, or let's just call whatever policy we want to compare as pi e, right? So the value, performance suboptimality of the comparator policy and the policy induced by your learn function. This can be bounded by, okay, I'll add the horizon. The Bellman error under the comparator policy plus the Bellman error under okay, under the policy that you learned yourself. Okay, pi f is the greedy policy that you define with respect to whatever value function you learn. And remember, pi e is just the comparative policy you want to compare with. Right.
The second one, is it h plus 1 for the first f inside the brackets?
Right, so like there's a small notation switch because I switched to the finite horizon case. So so here h is the horizon of your MDP. It's not the iteration number of your algorithm. Okay, so this is basically saying then let me clarify a little bit. So in the finite horizon setting, the function you learned at each iteration, t, is basically a collection of value function for each horizon. Okay? So it's all in the same iteration of the algorithm. It's just whenever I want to back up my value function, it's like, okay, f1, I want it to be approximately like the Bellman backup at the next time stat. So this is exactly a Bellman error because I'm not using the value function of my previous iteration as a target. This is, you can just think of this in the discounted case. It's like I do the Bellman error minimization of the value function in exactly the same iteration. So the analysis for discounted case is a little bit annoying, so that's why I switched to finite horizon. And yeah, there's a little bit notation switch. Thank you for bringing that up. So yeah, again, let me highlight. So you only need to be accurate on these two distributions. And that's it. Okay? So let me say I'll prove some of this if we still have time later, but let me just say how to bound these two terms. So the first term is actually very easy. Why? Because we just said, right, the offline distribution covers the whatever the visitation distribution that you want to, of the policies that you want to compare with. So I can just do importance weighting in this case, right? I can switch from d pi e to mu and pay additional importance ratio C. And okay, I'm gonna add a square, right? So because like whenever I minimize, first, you can only do importance ratio switch if the thing and in the expectation is non-negative, right? And also, remember when we do Bellman error minimization, we're doing the square error, right? So
That was just by the Cauchy-Schwarz inequality?
yes.
So before you did the rest of, how do you get the first term?
Oh, this term?
Yeah.
Yeah, I'll
Okay, you're proving now.
I'll prove later.
You prove later, okay.
Yeah. If we still have time.
Okay.
Yeah. So then if you look at this term, this is exactly the thing I've been minimizing with my algorithm on the offline data, right? I've been minimizing my square error on exactly the same distribution I've been doing so far. So you should expect this term to be like about like 1 over square root of n, where n is like number of data you have. And for the second term, it's this term is a little bit tricky. So why? Because if you look at this term, it is saying like this and this are the same function, right? I want to minimize my Bellman error under the policy that I induced, but this is unfortunately not exactly the same distribution as d on, because d on is collected by the policy of the previous time step from pi 1 to pi t minus 1, right? So my f will be accurate on all the previous policies with Hessian distribution, but not necessarily on myself. So then we kind of need to make some additional structural assumption that is saying, if I give you a reasonable value function class and you are in a solvable MDP, then there will be not too many times of distribution shift between all your previous policies with Hessian distribution and your current policy distribution. So another way to say that is, if you do everything correctly, at some point, your current policy, if I gave you a policy, the visitation of that policy can be right as a convex combination of some other policies' visitation traces. So then, with that assumption, basically this term is saying, okay, I can only incur big error for, say, let's say I only incur error for d many times step. Then this term is basically bounded by, okay, c, this is c, pi, e, and this is bounded by d over square root of t.
This, so that, what you said was very interesting, maybe slightly out of scope. Is this sort of this d coming from something like the Carrier-Theodori theorem?
No. So, well,
I guess whether
yeah. Let me say more. So, so let's think about our favorite tabular case. Okay, how many distribution shift that you can ever hope to incur is stay s times a, right? So like all policies with Hessian distribution can be written as a convex combination of s times a different policy state and action distribution. If you think about linear MDP, then it is saying, okay, I can pick the visitation distribution that covers each basis, right? Every policy's visitation distribution can be written as like a D convex combination of others. So you can generalize this to beyond, like to a very general setting that is called Bellman rank or bilinear rank. So, but basically that's the idea. But let's just say in the tabular case, okay? This only happens as times a linear steps. So then we're good. This term is also good. So basically it is saying, okay, now I can control these two, the Bellman error under these two distributions, and basically I'm done.
Can we think of this being related to like a mistake found in online learning?
Yes, exactly. So another way to think about this is like, for example, what if I do, let's say I switch all the value learning to model learning, right? So apparently like this error is not convex, so I cannot invoke like online learning no regret guarantee. I'm still doing online learning, right? Every time I minimize my error, it's just my loss function is not convex. So I cannot say, okay, I always have no regret guarantee. But if you say somehow I do model-based learning and I have like a convex loss function, the second term immediately gives you, okay, I will have like, maybe I pay some like range, Lipschitz kind of terms, but the second term immediately tells you, okay, I will always have no, like my regret will only accumulate with a rate of square root of t, right? But unfortunately, we have to make this additional structural assumption because the loss is not convex. So there's other subtlety that prevents this from working. You can say maybe, okay, what if you do like some non-convex online algebra algorithm like follow the perturb leader? It also doesn't work. We tried. So, but the bottom line is like the assumptions such as like a bilinear rank or Bellman rank, they covers a very wide range of problems. So it's actually pretty general because if you think of, even if you do like deep learning with RL, it's like there's no way that if I keep running my new policy, like my previous policy's data is not covering the new policy at all, right? Your error at some point, it always converge. So this is like something that actually can be reflected in practice. Okay, we have 10 more minutes. I will prove one part of this lemma. It's actually also quite similar to things we've been seeing before. So it won't be, will be pretty familiar for you guys. Okay, so what do we want to bound? We want to bound the difference from pi e to pi f, right? We want to bound the difference between these two terms. And I'm just gonna subtract. I'm not even gonna write max. Oh, I need to write max because I'm doing a Q function. Okay, let me add max. Okay, I'm just gonna plus and subtract and add the learned value function. Okay, so to bound, so I'm just need to bound this term and this term separately. And bounding them are actually like pretty similar, so I'm just gonna show one of them. So it's just a slight varied version of performance difference lemma. Okay, so let's bound the second term. So to bound the second term, I'm gonna be a little bit lazy. I'm just gonna write f, and I'm again gonna. Oh, I also need to add back the time step. So from S0, SA, max, A. Again, I'm gonna minus another term, which is the Bellman. Because if you, okay, let's take one step back. If you look at these two differences, right? So somehow in the end, the difference of this term will become this Bellman error. And this Bellman error will be the difference of these two, the second term, second difference. Okay? So I'm just gonna create something that is look like the Bellman error. Okay? So basically, I just subtract and add the Bellman backed up function of the next time step from like horizon 0 to horizon 1. So I'll leave this term here, okay? And this term is basically, then I'm just gonna expand this term, right? Remember, like, this term, okay, I'm just gonna expand them. So this term is just R SA plus the S prime sample from PSA next A prime F1 S prime A prime, and this term is just everything is basically the same, right? Except the functions that you are backcopying on is different. So prime or okay. So I'm gonna switch so this max A prime is basically like your policy action distribution at S prime, right? And for the V0, if you do one step Bellman backup, it's basically V prime F S prime V right? So what I did is just I expand the definition of Bellman backup on the function I just learned, and I get this guy. And here I just use the definition of the value function, which is basically also the one-step backup with the true value function. Okay, what do we have here? So now we see there's here is the Bellman error difference that we just showed. So we can always, okay, to see why it is the distribution of the value function you just learned, always remember, like, whenever I take max A according to my learned function, this is exactly like I take an action according to the function I just learned, right? Because the function, the policy I just learned, it will always take the argmax action at the state according to the value function, right? So now we kind of have the recursion, because you see here is the Bellman error term we want as the initial time step, right? And then here we have the difference between these two guys on the next time step, which is exactly the recursion here, right? This is the difference between your learned value function and the true value function for the same policy as an initial time step, and this is the second time step. And if you do the induction, you will see this is basically I sum up with the horizon, and each time step I will get this Bellman error on the respective time step. Yeah, I hope this is not too confusing. Like basically, this is exactly the same flavor that we've been seeing for like simulation lemma or performance difference lemma, right? So it's like every time step I will have like some additional term plus a recursion, right? So the recursion happens here. This is time step 0, and this is time step 1. The difference between the learn value function and true value function.
Yeah, maybe connect it back. If you remember when we were doing the analysis for like agnostic system identification, right? We had these two different terms, one on the experts distribution, one on our own distribution. We bounded each by the simulation lemma. What you're just doing here is the kind of model-free version of that. He has this thing that depends on the expert, the first part, and the thing that depends on what you went, the learner, and he's bounding it via something that is not exactly the performance difference lemma, but is a kind of another way to bound difference in terms of Bellman errors.
Yes, thank you. Yeah, and this term basically you can bound using almost exact the same technique. And I know like the writing is a little bit messy, but like there's a note on the website that has everything typed out. So, yeah. So again, okay, we're out of time. To recap, right? What distribution we want to minimize the Bellman error on? If we do hybrid RL, you only need the most realistic coverage assumption. And remember, like basically the key is this lemma is saying, okay, if you minimize your Bellman error on the offline distribution and your current distribution, that is sufficient for you to achieve like a comparable policy with respect to the best policy covered by your offline data. And I guess it's also saying, in some sense, as long as your offline data has good property, all you need to do is to do some greedy policy improvement during online. That's all the content I want to cover. And thank you, everyone.